wenn du willst, komm kurz runter, von da sieht man es. Das ist klar. Na dann, kündigen wir dich mal an. Hello and welcome to Source Code Optimization with and by Felix von Leitner. Have fun.
Good evening. So this talk will mostly be about C and C++ source code level optimizations, and I will show what they look like in machine code. So I will have assembler listings, and most of them will be for AMD 64, but some of them will be x86. You should have no trouble reading them because the instructions are kind of easy. So I chose them so it's readable. The main thrust of this talk is that many people do unnecessary optimizations on the source code level that make the code less readable because they think that in the end the generated machine code will be faster, and in many cases that's not the case. So I did some tests, and basically I just ran them through the compiler and looked at the code. So I might not have the best examples here, and I encourage you to do the same. So if before you do some great optimization, you should do a small test case and run it through the compiler and look at the generated assembly code. It's fun. So the most important thing I'd like to say is that optimizing is important, even if I'm arguing against most of the optimizations here. Optimizing is important, but in most cases, keeping the code readable is more important. And you should learn what your compiler does for you and then help him do it and not get in the way. And that's the most important optimization you can do. And I'll start off simple. So let's say you want to define some numeric constant, in this case 23, and there are several well-known ways to do that. And it's not always just about readability, it's also about debugging. So this is kind of famous, so it's just a warm-up. So the thing that most people do is they just use hash define. The problem is that the symbol, in this case constant, doesn't actually reach the compiler. So it doesn't show up in the object file and not in the debug symbol, so in the debugger it's not available. So many people still do this because they think it's the fastest. Alternatives that are also well known is to use const int, and this has the advantage that the symbol is visible in the debugger, but it has the disadvantage that it actually allocates this number in the data segment. So we can work around that by using static. I will show the code on the next slide. The next alternative is kind of tricky, but it's also a well-known hack from ancient C times. You can use enum, and in this case, it doesn't use any space and is visible in the debugger, so many people use this. So let's see what actually happens if we do this. And I wrote this little code, and you see I add a different number each time, so the compiler doesn't use common sub-expression elimination. So I want to see if any of these actually generate a load in memory, and you can see the compiler always calculates the sum and puts it in the binary as a constant. So in all of these cases, it doesn't matter actually what you do, you get the same efficient code, and you get no loads. So even in this case, when you say it's a const int, it will allocate memory. If we say static, the compiler can actually remove that. I have some example for that too. But you see, in all cases, the same code is generated. So most of the tips that float around that are, or in optimization books, what you should do to get faster code, don't actually work. So you should always question tips and look at the output of your compiler yourself. By the way, I'm saying compiler, and I usually mean GCC. I'm using GCC on Linux. I also tested the Intel C compiler and the Sun C compiler. Different compilers obviously do different things, but you should use your compiler and not just believe me. So I did most of these tests with GCC and the other two, and in cases where the result is different, I hope I won't forget to notice, so to tell you. So this is another example to show the difference between static and non-static const int. So you see that I have two ints here, 23 and 42, and I have this function that returns the sum of them. So you can see that the compiler, this is the code that's generated. Again, there's no loads for neither of them, but you can see that A, so the non-static one, A actually gets put in the read-only data segment. So this wastes a little memory. The question of using hash define versus some other method also applies to using inline functions. And some people use preprocessor defines to do inline functions. So they say this function is called so often or it does so little that I want to save the call overhead, and they use the hash define macro. For example, the abs function to calculate the absolute value of an integer is usually done in a define or as an inline function because it's so small that the call overhead will dominate it. So this is something that's used often, but if you use hash define, you get the same problem that you get with a hash define for constants. The preprocessor resolves it before the compiler even sees it, so there's no symbols in the debugger, and you can't compile without inlining and set a breakpoint. So if there's a bug in your inline function, there's basically no way really to find it in the debugger. So one thing with inline functions, many people think they have to write the word inline. That's a keyword in GCC, and C99 also has it. I have slides on that. You don't actually need to do that. So, but if you do it in GCC, then you will actually get two copies of the code. You get the inline copy at the place where you use the inline function, where you call it, and you got a separate version in case someone uses the ampersand operator to get the address of the function or calls it from an external module. So unless you use static or extern, you get a useless copy. And that's why GCC doesn't inline per default in -O2, because it will generate more code. But if you use static, then it won't generate more code if you call it just once. So GCC will inline even at O2. So let's test this macros versus inline things on these functions. I wrote the same code basically once as a hash define and once as this inline function. And then I have two functions, foo and bar, and one of them calls the hash define version and one of them calls the other one. And you can see I didn't write inline here, but it still gets inline. And not only that, the generated code is exactly the same. Right? So this happens lots of times. Actually, this code is pretty smart if you can appreciate the niceness of this code. I was surprised to see that all three C compilers generate the exact same code for this. And this is tricky because it doesn't have any comparisons or conditional jumps in it. So this is a jumpless sequence, which is usually people try to do this by hand in C once they reach a certain optimization level, but even that you don't have to do by hand. So this is good because conditional jumps are really tricky to get right in CPUs, and they have a lot of overhead in the CPU to predict the outcome of these branches. And in functions like abs, you usually don't know in which way it will be resolved. So this is a difficult thing, and the compiler knows this and generates good code in both versions. So we see there's really no advantage to using hash define for inline. There are some cases where you still will have to do it. For example, if you use alloc A and return a pointer or want to return a pointer to the alloc A stack structure, but that's so rare that you shouldn't really use that excuse. Inline in general, so I already mentioned it, you don't have to write the word inline to get the compiler to inline your code. The compiler will inline anyway, and if you use inline and the function doesn't inline very well, for example, because it's big and it's called all over the place, then the compiler might even ignore your inline keyword and decide that the code is better if you don't use it. So it doesn't make any sense, it doesn't buy you anything, don't use inline. But do make the helper functions static if you want them inlined. So the downside to inlining is that it destroys code locality. I have some statistic later in the talk about how memory bandwidth is really the dominating issue for optimization these days. So only use inlining when it actually makes sense, and one of the places where it does make sense is for range checks. I have some statistics on that too. So there's some subtle difference between inlining in GCC and C99. So the difference is whether a separate copy of the function is output 2. So if you have a small inline function and you use it once, then GCC, if you just say inline, will output 2 copies of the code. If you use static inline, then no symbol is exported because it's static to this static linkage. It means it's only used in this object file. So the function code is only emitted if an address of it is taken, and otherwise it's just inlined. And this is the same for GCC and C99. However, if you don't use static and just use inline, then GCC will generate a copy, but C99 will not. And there's extern inline too, but as I said, you don't really need to write inline, so this is just to tell you, if you use inline, you can shoot yourself in the foot because it means different things in different versions of the compiler. So just don't use inline. So there's another thing about inline, the thing that you try to optimize away with inline functions, the call, is actually pretty well optimized in modern CPUs. Modern CPUs don't have just the usual stack that's used for the arguments of functions, but they have a separate mini stack in the CPU that just caches the last return values. And these values are used to prefetch the code, and so it's actually like a conditional branch, and the CPU uses the same branch prediction logic. But the prediction is easy for calls usually because the return value never changes. So the CPU has this internal stack with the return values, and if the value is still the same on the stack, which is the usual case, then it's already quite optimized. Only if you use some kind of, if you get exploited, for example, or if you fuck something up, then the return address on the stack will not be the same, and then it gets really slow. So modern CPUs already have mechanisms to make code fast if you have many calls, and you can see this best if you use the -f pick flag, which creates position-independent code, and you have a target CPU of i486 because they didn't have this optimization. The later CPUs usually have. So everything 686 or later has it. So you can see that if with pick code, the problem is that you have to use your own address where the code that's currently executing lies in memory and calculate the difference to the GOT, which is a known value by the linker, and to access other symbols. So the compiler, if I use position-independent code, actually has to generate code to look at the instruction pointer to see which code is currently executing. And the best way to do this is to call yourself. So this call just calls this label here, which is 0 bytes distance, and then pops the value from the stack and gets the return value. So this destroys the CPU internal cache of the return values I just told you. That's why if you use -f pick on later CPUs, you get different code. So this is the code that's generated now. You get a call to this little function that just moves the return value in the register and returns. And this is actually a lot faster. You can try this at home and see. So the CPU is already quite efficient, and I did some small benchmark. So I put this on the right to indicate it's in a separate file. I have this function. I put it in a different file so it cannot be inlined. And so what you can see is that I have this function foo that basically does nothing. This call to foo will probably be inlined if you tell the compiler to use maximum optimization level, right? So I put this function in a different file, and it does really nothing to get at least one call in this. So what this will do basically is iterate 100,000 times and just do basically nothing, just a small increment on the static variable. So you can see the timings here. The loop takes only 4 cycles per iteration for the call and the return. So if I inline this, that's just 4 cycles that I save per call. And to give you a perspective on how much that is, one iteration of MD5 takes 16 cycles per byte. So you can see this is really not a lot. MD5 is a very fast cryptographic hash function, and that so you can see on AMD there's actually even less. So inlining had big reasons for existence a couple of years ago, but these days CPUs are quite good. So leave the decision what to inline to the compiler, and don't touch it because you will usually make it worse. So this is the single most important thing I'm going to tell you today. Many people think that range checks should be optimized away and you just leave them out when you think that your code will never touch them anyway. And this is one of the major sources of security problems these days, that people think they shouldn't do the range check here because it will never be triggered anyway, and it would just make the code slower. So compilers can actually do a range analysis on loops, on the variables on the loop and in the loop, and see if the range check will be triggered or not. And in the cases where it will obviously not be triggered, it can actually not generate code for the range check in the first time. The compiler can do common sub-expression elimination to eliminate duplicate range checks. So even if it's necessary in one place and you do the same check below, for example, because you do it in some kind of inline function, then the compiler will only do it once. And if you check something that's invariant to the loop, then the compiler will move the check out of the loop. So all of this is done, and it's been done for years. And let's see how it works. So I wrote this little test code. I have this array. It's, again, 100,000 elements. And I have the code that writes directly. To every element, it writes a 0. Right? Easy enough. And then I have this indirect version. I declared it static, so it will be inlined. Right? So I have the separate thing that does the same, but has a range check. Right? So this is the code that's generated for the loop without range checks. And this is the code that's generated for the version with range checks. You see, the difference is that one writes 0 and the other one writes -1, but that's it. So if you are in doubt, do the range check. The compiler will remove it for you if it's not necessary in most cases. And even if it doesn't remove it, it's usually, that's not the reason why your program is slow, right? So what compilers cannot do these days, or at least GCC, they cannot inline code from other object files. So it makes sense, and that's one of the few cases where I actually say it does make sense to use inline, or explicit inline even, to use range checks in inline functions, because then they will be optimized away. GCC is pretty good at that, and the other compilers too. So I did some tests. I used some other compilers, and I used the Intel compiler, and it's actually funny to see how their optimizations are really benchmark related and not actual code related. So ICC looked at the first code that initialized everything with 0, and used SSE, the vector extension, to write the zeros faster, which is complete bullshit because it's all waiting for memory in the end. You know? So it's not going to be faster, but it looks better. And the compiler actually says inline one loop on standard out. So you can see that how good it's optimizing. The second loop that does the same is not optimized with SSE. So if you use -fast, then which is like the do all optimizations option, then the Intel compiler is actually intelligent enough to see that both loops write to the same data and not do the first writing at all, which is kind of funny. And so the Sun C compiler is even funnier because it unrolls the first loop and does software pipelining, but doesn't even inline the small function. So you get varying results with different compilers. So again, use your compiler to see what happens for you. But in general, you can say that range checks should not be left out because they might hurt performance. Another thing that people usually do is that they try to come up with clever ways to write common operations. So for example, in this code, I want to divide A by 4. And some people know that this special case can be written as a shift. And as you can see, the compiler knows that and already does the shift for you, right? So this is a slightly contrived example because there's a very efficient way to do this on x86. And so you can see this is just one instruction, which is really low defective address. So this adds 17 to the result of RDE plus RDE times 8. So this is actually times 9 and adds 17. So you can see if you try to write this better with shifting and whatever, then actually the code would be worse. So usually, in particular with complex instruction sets like x86 and AMD 64, the compiler is usually better at finding this stuff than you. There are examples, counterexamples, and in those cases it makes sense. But if you are not completely sure that you know what you're doing, please look at what the compiler does before optimizing and after optimizing. And if you make it slower, then undo. So I did a slightly bigger example of strength reduction. So this array is an array of int. So if I access one integer in it, like the 5th then it's not just adding 5, but I have to multiply by the size of each element, which is 4 or maybe 8, depending on the architecture. So, and to make it slightly worse, I add 2 in each loop, right? So this is the naive version. So the fast version would probably try to use a pointer and not use this array indexing here, but you just you pointer arithmetic in the loop, right? So this is the slowest and easiest way you could possibly write this loop that just adds 10 integers from this, and it doesn't start at offset 0, but it adds 2. And you can see the compiler already, this is where the +2 is hidden in this instruction. So it doesn't even generate one additional instruction to have this +2. So if you did something manual, this code would be bigger and slower, right? And you can see that the compiler moved the first sum out. So what I'm doing is I initialize sum to 0 and then add the first element in this loop, right? The compiler detected this and just removed the initialization with 0 and just copies the first element of the loop. So if you try to make this better, you will probably make it worse. So maybe no one asked this yet, but I was stumped when I saw this. This works around a bug in the Opteron processors that cannot efficiently predict the return address of this call if there's a conditional jump that's not taken in front of the ret. And the AMD optimization manual says you should put this useless rep here and then it will be faster. And then put this in just to show you how much know-how the compilers have about your CPU these days. How many of you knew this and would have done this too if you wrote it in assembler? I have one. So you can see the compiler is usually pretty smart, and if you try to compete with him, I have this competing attempt to implement the same thing. So this time I'm trying to not do any array subscription stuff, and I do the same optimization that GCC did. I copy the first one and not initialize with 0, and I do some funky, unreadable pointer arithmetic crap in the loop. And you can see, if you just watch the right half of the display, you can see the code is actually a little bigger. And I think most people would agree that the left-hand side is more readable here, right? So usually the more stuff like this you do, the less readability you have, and you gain nothing really from it in most cases. Another thing that many people think helps, but doesn't at all, is constant folding. I have this example. This is also quite contrived, but if you look at the wget source code, for example, you can see an example of this. And you know, people used to make fun of it, and even I did make fun of it, but it's actually better than this. So if you see something like this, where someone adds 18 and then has this strange sprint, and the auditor has to count the possible length of this and say 1, 2, 3, 5, right? And oh, my proc, and so you have to chase my name and look, this is 1, 2, 3, right? And then you find out, oh, the 18 was correct, right? So the other way to do it is to try to write it explicitly. And in this case, you can see, okay, uses my name has the length of my name, uses s has the length of s, and the only thing you really need to compare, which is easy visually, is if this is equivalent. Right? So this may look stupid, but actually it helps guys reading your code. So if you have the option of leaving it there or just trying to calculate in your head, which usually breaks down at the very least when someone comes and tries to internationalize your code. So this is usually a bad thing, to have some magic constants in your code. And it's even worse, I've seen this too, that someone took this 18 and has defined for max length or something, or length for this, and then so there's no magic constant in there because the style guide says you shouldn't have magic constants. So this is even worse, obviously. There's another thing that you usually see in code, and I'm guilty of all of these, I have to tell you this. So if someone thinks he can be funny and email me examples in my own code where I do this, I know, right? So this is why I investigated this, to find out if it's really worthwhile. So this is one of the examples that was useful in the late 70s and in the early C compilers, but these days not so much. The compilers just ignore the keyword usually, and save yourself the effort. This is something that's very important for the functional programming people, but it also is important for C. So factorial, one of the first things you implement in a new language. And you can see this is the recursive implementation. The function calls itself. This is a special kind of recursion because the last statement in the function does the recursion. This is called tail recursion, and it's easy to detect. And it's in compiler writing 101, they teach you how the compiler can detect this code and generate a non-recursive version out of it. So either you can waste like an hour, I don't know how good you programmer you are, to try to come up with a non-recursive version yourself, or you can just let the compiler do it and leave it in here, right? So there's some other stuff. So there's a story to this. So let's first look at the code. I have this is like a linked list thing. I didn't put any payload in, but you get the idea. And I have this code. I have this code that does some pointer manipulation on the list. So this is like a remove or something. I just wrote something. It doesn't make sense, but you get the idea. This is the code that's generated for this void foo. And you can see that there's two moves that read and dereference next. So I told you that the compiler does common sub-expression elimination, so why doesn't it do it here? And the problem is that this next that's written here, the pref could point to n, and then the next would change. So this is called aliasing. In C, usually if you have any kind of pointer stuff, then the compiler cannot know that this statement doesn't change this next. And there is, if it's function arguments, then there's some way to declare this in C99, but this is the one place where common sub-expression elimination actually makes sense to do manually. So in this case, if you know it's not changing and you use the same thing, then in this case would be one of the few examples where you could actually help the compiler. Yeah, but that doesn't help in struct definitions. The restrict is exactly what I meant for function arguments, but in this case, so that's why I chose this example. So this is called aliasing, and this is one of the reasons why Fortran is considered to be superior for mathematic code, because Fortran doesn't have pointers and no aliasing, so the compiler can just assume that there will be no aliasing. One of the other things that people are hoping the compiler is doing for them is removing dead code. And the compiler and linker actually have some, they make some attempt to remove dead code. For example, if there's unreachable code within a function, so for example, you have a switch statement and you check for one element twice, then the compiler detects this, will probably emit a warning and not generate code for the second one. Or if you have like a break in a function and then another statement below that, or a go to somewhere and then print whatever, then the compiler will know the print can never be hit and not generate code for it. So the compiler can do this within a function. And if it's a static function that's never referenced inside the same file, then the compiler cannot, can just remove it from the object file. But if you have a function that's not static in some object file and it's not used by someone else, but some other part of the object file is used by someone else, then the compiler has to leave it in. So you can either have the whole object file used or you can have not used, but you cannot use a part of it. And that's because the object files are more general than the C language needs. So you could have, for example, inline assembler that calculates some offset manually and then jumps somewhere and does reach the print or something. So there could be reasons like pointer arithmetic on function pointers, stuff like that. So the linker doesn't know that, you're not using that. And so if you write a library, you should put every function in its own object file, so this optimization can work in the linker. Note that function pointers do count as references, even if the pointer itself is never used. So the inline assembler is another thing that people tend to like to use. And what's saving us from this most of the time is that it's really hard to use the inline assembler in GCC. So if you looked at the manual, that's a pain in the ass, and most people never really get to it. So if you do something wrong, then the compiler will use your inline code, but will assume that the register you used was not touched, and then put some value in there. But only after you change something else in the code, and suddenly the result after the inline assembler statement is wrong. Or you can have stuff like the inline assembler statement is moved along because you forgot to declare that it modifies memory, and the compiler thinks, well, it doesn't do anything, so I can move it around. So most people cannot do inline assembly in GCC, and that's a good thing. So most of those who can do it don't actually improve performance with it. So the case in point in this instance is MatPlay, which is an MP3 player, and this is the code that shipped with MatPlay, and I think it still ships with it. So if you read for example, the AMD optimization manual, this is like an ancient instruction that was used to have 64-bit arithmetic and do a shift on it. And it still makes sense to use it if you don't have any temporary register. But if you do have a temporary register, this sequence is much faster. So what this does, actually it turns out that the guy used this statement not to make something faster, but because he didn't know how to do it in plain C. And there is a way to do it in plain C. So just this change from this statement to these three statements had a 30% performance impact on all computers I had access to. The guy wrote me that he has a Pentium 4, and on that architecture has the same speed. So apparently there's no fault for him on this point, but you should read all the manuals and try to make code run fast everywhere. So, oh, and this is what I mean when I say it's hard to do inline assembly right. This is still could be considered wrong because there's no volatile here, so the compiler could still try to move the statement around and break something with it. But I'm just mentioning this so you can see this actually everything of these is actually needed here. So this is how you would do it in C. I used the same identifiers, that's why the underscores are here. I'll show you again this one. So you have low, high, and result. So this is how you would do it in C, and this is the code that the Intel compiler generates. And if you look closely, you can see it's the same code that my improved version of the inline assembler statement would have used. Unfortunately, GCC sucks with 64-bit arithmetic on 32-bit platforms. So with GCC, you didn't get this good code. You actually get the SHRD using code. But that's what I'm saying. You should always look at what your compiler does. But you could have done the same thing without inline assembler and it would still have worked just as fast as the current shipping version of MatPlay. Another thing, this is the first time I actually understood that inline assembler is not necessary. So the Intel and most other architectures have instructions to rotate the bits inside the word. So for example, if you shift something, you will fill the new bits that are, if you shift left then by 4 bytes, then you have 4 bits, then you have 4 new bits on the left, and they will be 0 filled. And rotating just means that the bits that fall off the right side get put in on the left side. So that's something you rarely use, but sometimes people need this, and there is no way to express this in C in a good way. So what you have to do if you use C is you have to do the shifting and ORing yourself. And it turns out if you do that, the compiler detects it and generates the OR for you. So there's, again, no reason to use inline assembly here. And this looks pretty hairy, but as you can see, the compiler is usually smarter than people give it credit. So this is more of a C++ thing, but it also makes sense in C with older compilers. If you do an A++, what the hell? Shut up. So if you do A++, the compiler usually has to create a temp copy of A, which it usually doesn't in C because it's built-in types like int or pointers, and then the compiler can do it usually without creating a temp copy. But in C++, this actually makes sense to use ++A instead of A++. This advice was also good for C in the 90s, but today, even in C++, it doesn't matter. So let's come to the optimizations that do matter. And one of the optimizations that actually do matter has to do with cache lines. So in the CPU, there are several levels of cache, and they usually have cache lines and associative caches. You can read up on this in CPU architecture books. So the point to understand about this is that several pieces of memory map to the same cache line in the cache. So if you have a data structure that has the same size as the cache line and you walk through the cache, your array, then it might be that every element of the array actually hits the same position in the cache line, and you lose all the cache efficiency. And this is known to happen in big matrix multiplication code that they use to benchmark supercomputers. So this is why this is well known. And the thing you have to do if that happens is to add dummy byte to each element in the array, and then it won't align anymore and it will be faster. So this kind of thing is something the compiler could be expected to do, but doesn't right now. Fortran compilers on supercomputers are known to do this, but I know no C compiler that does it, in particular not GCC. So there's some optimizations I'm saying that actually do make sense, but most of them don't. So my personal pet peeve is people who just coming from university know every fancy algorithm there is, and they have this, you give them the task to sort 100 file names in LS, and they use like a self-balancing whatever tree with like, I don't know, and usually this is like several screen pages of code that you just would have to read, and it not only doesn't it make it faster, it also has more overhead because trees have next pointers and left pointers and child pointers, and all of this stuff pollutes the cache, and in reality it's usually fastest to do it the simple way. So if you see someone use Fibonacci heaps, just shoot them, okay? If you do manage 1 million elements, then you should use a proper data structure. But that's so rare that in most cases don't. So my rule of thumb is if the data structure can't be explained on a beer coaster, then it's too complex. The only actually really important optimization goal these days is memory latency, and I have these values for you. If you use multiply instead of shifting, which I showed you the compiler already does for you, fixes for you, but if the compiler wouldn't do this, that would be a 5-cycle penalty. I showed you the call penalty is 4 or 3 cycles, depending on the CPU. So 5 cycles if you use mul instead of shift. If you mispredict a conditional branch, it's 10 cycles. But if you access main memory and that's not in the cache, that's 250 cycles. So you can see all the stuff you do with, oh, let's make a shift out of this mul, that's really the utter wrong place to optimize. In most cases, you should try to make your code and data structures as small as possible so it fits in the cache. And if you have done this, then you can look at the rest. So keep this in mind when you do optimizations. There is some commercial profiling tools that try to tell you on which parts of your code have many cache misses, but AMD actually has one that's supposedly free and downloadable, but I didn't get it to work. It's maybe the Windows version works, but I don't develop on Windows, so I don't know. Intel has one that costs money. Maybe they give it away now too. They give away the compiler after all, I don't know. But this is really the only really important thing to optimize for. All the rest that people spend weeks and weeks of their life doing with inlining functions here and trying to restructure code there, usually the only thing that actually matters is the main memory misses and cache misses. So that's basically all I have to say. If you do an optimization, test it on real-world data, and if it doesn't work, undo it. So if it's not drastically faster, but just a little bit faster, but make the code unreadable, undo it too. Because usually, people won't even notice the difference in speed, but they will notice if the code is unreadable, because then security problems will not be found and will hit you later when you can less afford them. Any questions? Okay, so one?
Actually, not a question, but a comment about cache misses. Valgrind should have a tool for it, CacheGrind.
Oh yeah, you're right. Valgrind has one. That's right. Is it any good? I've never used it. I just know it exists.
Didn't try it either.
Yeah, I don't know. So that's right. Valgrind actually has one as a tool for that. And everyone should be using Valgrind anyway. Plug. So use CacheGrind too.
Any more questions? Ah, there.
I put the slides on the webpage and upload it to the Congress web pages too, so don't worry. If you missed anything, you can still email me. And the full house.
There's a GGC extension, as far as I know, called likely or unlikely, which you could use in conditional statements. Did you make any research on that, or can you give recommendations?
I've never used it, so it might be interesting. Can you email me a link or something? I'll check it out and put it on the webpage too.
Okay, I will do. Thanks.
Okay, thank you.
Have you do any kind of analysis on runtime optimizations like Java Virtual Machines does or wherever, you know, there's a lot of optimizations like automatic inline, unrule lobs, everything that Java Virtual Machine does, and it's really amazing. Have you studied something of this?
I didn't quite understand the question. Have I done it with Java? Was that the question?
If you have to do some analysis of the Java Virtual Machine optimizations, that is doing all of this, but in line. You know, they are doing on the runtime.
Oh, if the argument is calculated at runtime instead of the constants, you mean?
Yep.
Yeah, well, then the compiler has to do the actual code to add, but I just did the constants to show you that no matter how you do the constants, the compiler always does not have to generate any adds. But if it's runtime generated, the values, then yes, the compiler will have to actually do the add.
There was another question. Who was it?
Why did you pick optimization at the topic? Because in most cases, I think people have more problems writing correct code, and it doesn't matter to optimize when your code still contains many bugs.
Yeah, that's right, but I think it goes hand in hand because in most cases the bugs come from people trying to be more clever than they should be. And I'm saying don't try to be more clever than your compiler because usually you aren't. And if you don't do self-balancing red-black tree crap to sort 10 elements but just use qsort and an array, then you will have less bugs. So, yes.
So my question is, when the compiler generates 64-bit code, is that really faster than 32-bit code?
Well, that depends on what you're doing with it. So, for example, if you do big number arithmetic, then it's a lot faster because you get more done per calculation. But if you do something else like graphics code, then there might be a benefit or there might not be a benefit. But if you ask on x86 versus x64, then x64 has more registers, so it can do more, the compiler has more optimization opportunities, and I chose to use 64-bit code here in many cases because the code is easier to read, it's less code. You need less code for the same stuff, so I'm using 64-bit all the time.
Did you use any compiler optimization options?
In my examples, you mean?
Yes.
Oh yes, I always use like -02 or -fast on Intel. I use like the usual, I don't use any special stuff like -f, whatever, but I use -02 or -os, depending on, if I compile stuff for myself, I use os, which is like 02, but leaves out the optimizations that cause more code to be generated, because that's usually bad, because it uses up more cache memory. But in these examples, I usually use -02 and -f a mid-frame pointer. But no special magic stuff you couldn't try at home. So I think that's it. Thank you for coming.
There would be.
Oh, there's one last? Okay.
We've got a quarter of an hour left, so there's actually some time for questions. In university, you learn a lot about sophisticated data structures like red-black trees and AVL trees, and they really suck. But do you say they should be omitted at all, or as a rule of thumb, when should sophisticated data structures be used, and when should you stick to easier data structures?
I'm saying if you have reason to believe that your code will be used on huge data sets, then by all means use good data structures. But if you use, like for example, the STL standard string in C++ that actually uses a red-black tree of string fragments. And that's why if you have a small string and just concatenate another string, you will have like 100K of code that really does nothing. And you just have like 20 characters in your string, right? So in many cases, people just use overblown data structures and don't get any benefit from it, just get the downsides. So yeah, you should learn about them so you know them when you see them, but be very careful before using them.
I was reading some kernel code recently, Linux kernel code, and I saw that they use GCC extensions like the likely and unlikely definitions in if conditions.
That's actually part of C99. So this is
okay. I never saw that in userland code, so I wanted to ask if that really gains you something or if that's just like...
So these likely and unlikely statements, in case you don't know them, you can, for example, if you say if, and you have like a range check, and you can know that in most cases the range check will not be triggered because most of your code does the correct ranges. Then you can say if on the unlikely, and then the actual condition, and the compiler, you can tell the compiler with this that this jump is less likely to be taken, and the compiler can arrange the code so that the path that is usually taken is straight, in a straight sequence in memory. So this does gain you something, but only in a few places. And there is userland code using it. For example, glibc uses it, and mysmalllibc also uses it. But you know, in most cases, it doesn't gain much. But it's a habit. You should do it if you can. The problem is that most programmers are notoriously unable to predict how their code is being used and which is actually faster and what should be taken and what not. So it's usually easier to use profile-guided optimization in the compiler than trying to guess which one is likely and which is not. But in clear cases like range checks, yes, you should use those.
Do you actually have anything to say on the restricted keyword, or do you have you ever seen it actually do anything? Because I've tried like retrofitting code with restrict and it didn't do nothing for me. And GCC, of course. So.
Well, the C standard doesn't actually say you have to generate different code. It just says it's a keyword. So I think what they did first is just recognize the keyword and then do anything with it. But you can say you can construct functions where it matters. So for example, this foo function, where was it? Crap, what the hell? I have too many functions. Okay, I'm not finding it. The aliasing example, where was it? What the hell? Okay, you can look it up yourself. But so you can construct examples where it actually makes a difference, because the compiler suddenly does use the sub-expression elimination. So it does make sense, but usually it doesn't. You should still use it because, you know, later versions of the compiler might be slow, might be more intelligent, and you wouldn't want to go over all your code again if the compiler finally starts to really do something. So yeah, I recommend using it. Sorry. Okay, thanks for your time. I hope you learned something.